Okay, good afternoon. This is Torsten Kruse, Kruse Training, Kruse Analysis. Welcome to this afternoon webinar in regards to cause and effect behavior in injection molding. Let's get started. First, I would like to give you a quick overview. Cause and effect behaviors in injection molding. It is so important to really understand the behavior in injection molding. Yeah, there's so many factions that go into injection molding: part design, mold design, processing, the machine, the environment, and the technician who actually sets up the machine, that it is very, very complex, as we all know. So what we're going to see today is the cause effect behavior in injection molding. We just briefly talk about this, give you my opinion on what's important to learn in injection molding. Talk a little bit about a Kruse analysis, circle of knowledge training program, and then we go right into the topic today is processing and polymer flow during packing. This is very, very interesting subject matter. Most people overlook that, and I want to give you a quick overview of what to expect and what to look for when processing a material, and how to set up the pack, or how the pack pressure and the pack pressure profile will influence the volumetric shrinkage behavior inside of your molded part. We have a little Q&A, but if you have a question, you can type it in the chat room. Otherwise, you're always welcome to send us an email, and at the end of this webinar, you will have the address, or just go to krusetraining.com, where you can get the email address, and you're always welcome to send me an email. Don't hesitate. I am here to help. Let's get started. Understanding complex behaviors and interactions in the molding industry is critical in order to stay competitive and ready for the future. These are big words, and they have a really true meaning, basically telling you that injection molding is really complex, and it really is. If you really think about when a part designer from an OEM company is trying to optimize a design, they really have to do this in connection with the material in mind. So you cannot optimize a part design for a part if you don't know exactly the material and the material behavior. So are you designing a part for polycarbonate, for PC/ABS, for nylon, polypropylene, polystyrene? All of that is really, really important to know and to really understand the material's behavior before you try to optimize the part design. So having said that, molded parts really have some requirements. And some of the requirements obviously are dimensional tolerances, structural strength and requirements. You have to endure, the part has to endure. Then we have some appearance and aesthetic challenges that need to be met. Of course, acceptable shrinkage and warpages behaviors in the part, and assembly functionality. Those are just the basic requirements that are important to understand for the part designer to really optimize the part itself. So what Kruse Training is all about is basically trying to design an online knowledge system where you can go in and learn different subject matters in injection molding. Yeah, the Circle of Knowledge training program, it really is basically designed to help part designers, mold designers, and processors really to speak the same language, yeah, to understand what happens in injection molding, to make the right decisions when optimizing a part, a mold, and a process. So these are concise lessons that we have developed. Right now we have 96 available, By the end of the year, we're probably up to about 106. And then next year, another 25. So we get, by the end of next year, we'll get to 130. And every year we'll add new lessons to it. So that's really what we're all about, is trying to really convey knowledge to the injection molding industry to help you along to be better part designers, mold designers, and processors. Okay? So let's get into the lesson. It's lesson number 4, Polymer Flow During Packing. So let me grab my website, and this is how Kruse training will actually look like if you have a login. Some of you do, and basically you have all these lessons available to you for review, multiple review, anytime, 24/7, 365 on any device. But let's get to the lesson for today, Polymer Flow During Packing. So let's get started, listen to it, and I'll stop in between to give you some more background and hints, okay?
Understanding the impact of packing pressures on polymer flow is an important aspect of successful processing. Our goal in this lesson is to evaluate the predominant polymer packing flow path, which shows the areas of continuous polymer flow, specifically during packing and cooling. In this lesson, you will learn how to evaluate packing behavior by modifying the filling to packing switchover points and packing profiles. How to evaluate the predominant polymer packing flow path by evaluating tracer results, melt core, packing pressure and clamp tonnage, and volumetric shrinkage development.
That's very important. You know, as I said, we will look at different pack pressures and what they actually will do inside the molded part during the packing phase. We'll take the tracer results. We'll see what they look like. Yeah, they're very massless particles. They float around in the molten material, and you really can use those to see what I call the flow behind the flow. Yeah, the internal material flow based on the geometry of the material. Okay, this is really interesting to see that.
The bezel part for this lesson is shown on screen with the associated measurements. The part is molded in an amorphous PMMA polymer with an MFI of 4 grams per 10 minutes. In this lesson, we will analyze 2 filling to packing switchover points, the first at 95% and the second at 99%. This table on screen shows that for the 95% switchover analyses, the pack pressure profiles remain constant, and in the 99% switchover analyses, the pack profiles change.
Okay, so just to recap, it's a big table, I know, but we take this part you just saw and switched over from fill to pack at 94 to 95%. We have 3 different pack pressure profiles at 25 megapascals, which is about 250 bar, about 3,600 psi, as you can read, and 50 megapascals and 100 megapascals. So same switchover point, different pressure profile during packing. I will look at the tracer and the internals, what will happen. The second part is we switch over much later at 99 and have various pressure profiles. Here is a pressure profile that we start out with 25 megapascals and then decrease it to 5. Then the second one here is at 99% switchover with a constant 25 megapascal pressure profile. So you basically can take the number 5 and compare it to the number 1, yeah, and get a good comparison what the switchover point will do. And then the last switchover point, what we will do is we take the pressure from 50 megapascals all the way up to 100 with an increasing profile, okay? That is a little bit different. Okay, let's go.
Let's begin with the filling behavior for the sample part. There are no significant fill-related issues.
Simple to fill, no big deal.
The required injection pressure to fill the part is 45.3 megapascals, which is well within a molding machine's capabilities. There is a small pressure spike when the polymer reaches the gate. After the material enters the cavity, the pressure curve evens out without any further spikes or dips. In this lesson, we will analyze the packing behavior of the sample part by looking at the filling and packing tracer results, melt core, packing pressure and clamp tonnage requirements, and volumetric shrinkage development. As a reminder, tracers are massless particles that move during filling and packing and show the preferred polymer flow direction. Tracers are an inside look at the molten flow path.
Okay, just to stop here very quickly. So we look at the filling and packing tracer results. And what you will see is little dots moving around inside of the cavity. And pay attention to them, because you will find that from the gate, these tracer particles will fill the part, yeah, like you fill it with material. And then when the packing starts, you will still see little tracers continue to move. And that tells you that you have packing flow. And the predominant direction of the packing flow is really the key to understand how we add material to the cavity, okay? And that will have an impact on, of course, packing pressures, clamp tonnage, and the volumetric shrinkage differences. Really cool stuff.
Here you can see the tracer behavior in the first evaluation, with a switchover point at 95% and 25 megapascal constant pack pressure. The blue tracers indicate the path of the packing flow after the part is filled. Notice that the packing flow moves from the gate to the center section and then towards the outside corners. The flow stops between 8 and 8.5 seconds into the packing and cooling phase.
Yeah, you really saw this very nicely here, that the material fills the cavity, and you see some of the traces moving from the gate towards the center section, yeah, and then some of them moved along this edge here. Yeah. And it took 8.5 seconds for all of the tracers to stop. So basically you can tell that, hey, we can inject material up to 8.5 seconds in the area of the predominant flow path, basically the thickest section in the part. You'll remember, plastic flows the path of least resistance, and so does it in the packing phase. So where the thickest section is from the gate on into the part, that's where the tracers and that's where the material is going to go.
Polymer movement during packing is closely tied to mole thickness, so the molten core behavior should also be analyzed. Here you can see that as the part cools, the same corners that carry the tracers are the last to cool. Remember, packing flow only occurs in areas that are still molten. Now let's look at the packing pressure and the resulting clamp tonnage development for this example. The pack pressure of 25 megapascals results in a clamp tonnage of about 8.6 US tons. The curve shows the clamp tonnages decrease quickly, and there is no residual pressure inside the cavity at the end of packing and cooling. The volumetric shrinkage animation for the first example shows that the highest shrinkages are away from the gate at the end of flow, while the lowest shrinkages are closer to the gate. Here you can see a cross-section of the part showing the volumetric shrinkages of about 2.7% at the end of flow and about 1.3% near the gate.
Yeah, that's very important to understand in injection molding and for the processors. So how do we know what volumetric shrinkage we have? Well, you don't really know what volumetric shrinkage you have, but you will know what it does to the dimensions. So as usual in injection molding, the areas further away from the gate gets less pressurized. If it gets less pressurized, it has higher shrinkages, so volumetric shrinkages up. Near the gate, because the pressure comes through the gate, we have less volumetric shrinkage. But what really, really is most important is the range. Yeah? Our goal is to have a dimensionally stable part that has the same dimensions near the gate, at the end of the gate. If the range is minimal, that means uniform shrinkage, that's really our goal.
The first set of results is shown in the table.
And just one more time, 95% switchover A constant 225 megapascal packing allows the tracers to move and put material into the cavity for 8 to 8.5 seconds, causes a volumetric shrinkage range of 1.4%. Now let's take a look at the other ones.
Moving on to the second set of evaluations for the switchover point at 95% and a constant pack pressure of 50 megapascals. This animation indicates the tracers stop moving between 7 and 7.5 seconds, about 1 second before the previous example.
What?
Because this example has higher pack pressure, the clamp tonnage requirement will be higher as well. Here you can see the requirement to keep the mold closed is increased to 14 US tons, with the clamp tonnage curve having a different shape due to the internal cavity pressure. There is also residual pressure inside the cavity, and therefore slightly higher clamp tonnage at the end of packing. The cross-section indicates a significant reduction in volumetric shrinkage with the higher pack pressures. The volumetric shrinkage at the end of flow is about 1.9% and only about negative 0.1 to positive 0.3% near the gate. The results from the second analysis have been added to the table.
Now, isn't that interesting? Yeah. So a higher pack pressure, of course, will create lower shrinkages. We can tell far away from the gate, we reduced it from 2.7 down to 1.9%, and near the gate from 1.3% down to negative. What negative? How can that be? Well, it's an indication in an analysis software that you really pack the material near the gate. And guess what? The range is higher than what we saw before. So what is better? And we also notice that the tracers are moving now only 7 seconds to 7.5. So a second less. Well, that's the reason why with higher pressures, and let's now listen up, we compress the material in the cavity quicker. We get full compressibility faster because we use a higher pressure.
Here are the tracer results for the third example. With a switchover point of 95% and a pack pressure of 100 megapascals, which is twice as high as the required filling injection pressure, the tracer's movement stops between 6 and 6.5 seconds, 1 second earlier than the last example, and 2 seconds earlier than the first example.
Isn't that interesting?
The packing pressure and clamp tonnage graph shows that the required clamp tonnage increases to about 31 US tons. Note that there is still significant residual pressure inside the cavity at the end of packing of 15 US tons. The high packing pressure influences overall volumetric shrinkages. In this example, the shrinkages range from 0.1% to minus 1.6%. But most of the shrinkages are negative, indicates a severe overpacking condition. Both the residual cavity pressure that you saw on the previous slide and these negative volumetric shrinkages will create molded-in stress, possible stress cracks, and part warpage. High packing pressures could result in the parts sticking inside the cavity, creating possible part ejection challenges. The results from the third example have been added to the table.
That's significant. Yeah, we have a very high pack pressure. And please keep in mind what kind of material we are using. We are using a PMMA, an amorphous material that is really prone for overpacking if we do it wrong. And we definitely saw this in this case, that with 100 megapascals or 14,000 psi packing, we really compress the material so much that it is overpacked. And look at the range. It's still higher than the original range with the lowest pressure. And again, what's our goal? Our goal is to have uniform dimensions. So far I see uniform dimensions with the lower pack pressure. Yeah. overall the shrinkages are maybe higher. But guess what? If I know that, then I can upsize my cavity before I build the tool to a higher shrinkage, but therefore have a much better, more uniform behavior inside the mold.
To review, the packing tracer's movement shortens with higher pack pressure. This indicates that higher pressure compresses polymer material faster than lower pressure. Volumetric shrinkage ranges are lowest with the lowest pack pressure and reach an unacceptable negative range with the highest pack pressure. In the second section of this lesson, the switchover point from filling to packing changes to 99%. The pack pressure profile for the first example is set at 25 megapascals and is gradually reduced to 5 megapascals for the 8-second pack time. The tracer movement results indicate the tracers are moving until the end of those 8 seconds. The pack pressure and clamp tonnage graph shows a steep decline in clamp tonnage requirements immediately after the part is filled and is switched to packing. Then the curve declines gradually for the remaining 8 seconds until packing is completed. The cross-section shows the highest volumetric shrinkages near the gate. This is a common result when there is an early and excessive reduction in pack pressure. Shrinkages at the end of flow are between 2.5 and 3%, and near the gate about 0.3 to 0.6%. The next set of results have been added to the table. Notice that the decreasing pack pressure profile has a wider volumetric shrinkage range than the earlier examples.
So basically what it tells us, if we compare the first line with the fourth line, we still have the same pack pressure, but here we decrease it. So from 25 to 5 rather rapidly. Yeah. So this makes the volumetric shrinkage range go up, significantly go up. But it also tells us, as a processor on the machine, I have some control of the volumetric shrinkage inside the machine, with the machine, with the process. Is this an ideal scenario? Absolutely not. But again, keep in mind, we are starting to learn processing here in a little bit more of a deeper fashion. And that is a really important aspect to learn, that, hey, I do have some control over the volumetric shrinkage and dimensions if I use a packing pressure profile. It doesn't have to be that we start at 25 and go down to 5. We maybe go up from 50 to 100. Let's see what that does.
The next animation shows the tracer results for the constant 25 megapascal pack profile setup. The pack time is 15 seconds, and here the tracers stop moving between 8 and 8.5 seconds, which is the same as with the 95% switchover point analysis. The pack pressure and clamp tonnage graph again indicates a steep decline after the switchover point is reached, although in this example, the pressure remains on for 15 seconds to avoid the high volumetric shrinkages near the gate that we saw in the previous example. Here you can see that the high shrinkages near the gate have been eliminated. The shrinkage range is from 2.7 to 1.3%, and there are no negative shrinkages inside the molded part. The next set of results have been added to the table.
And as a reminder, the only difference between line 5 and line 1 is this is switched over at 95, this is at 99. So we have very similar results. So the switchover point in this particular case with low pressures makes little difference to the volumetric shrinkage and the range. Okay. Another key corner point for understanding how the process works.
The final example has a switchover point set at 0.99% and an increasing packing pressure profile from 50 to 100 megapascals in 15 seconds. Here you can see the tracers are moving until between 7 and 7.5 seconds into the packing phase. pack pressure and clamp tonnage graph shows the clamp tonnage goes up to 14 US tons, and the curve does not go down to 0 at the end of packing. The clamp tonnage remains at about 3 US tons, indicating there is residual pressure inside the cavity.
This could be trouble, by the way. Yeah, if you have the pressure monitoring capabilities on your molding machine, take a look at your in-cavity pressure sensors. You know, if you see that the pressure stays up at the end of packing, never goes down to 0, what it basically means is you're entrapping pressure in the cavity, basically overpacking material, trapping pressure, which can cause high residual molded in compressive stress, and it could also cause some ejection problems.
The volumetric shrinkages with the increasing packing pressure profile range, about 2.3%, from 1.5 to about -0.8%. The negative volumetric shrinkage behavior near the gate will result in residual pressure inside the cavity, high gate stress, and an overpacking condition. The final set of results have been added to the table. Notice that the shortest packing flow is achieved with the highest packing pressure. This is because the polymer gets compressed quickly, so the tracers stop moving. The longest packing flow behavior coincides with the lower packing pressures. The smallest volumetric shrinkage ranges are with the lower 25 megapascals packing pressure setups of either switchover setting. Lower pack pressure also results in positive volumetric shrinkages and no overpacking conditions. This concludes Section 5, Packing and Cooling, Lesson 4, Polymer Flow During Packing. In this lesson, you learned how to evaluate packing behavior by modifying the filling to packing switchover points and packing profiles. How to evaluate the predominant polymer packing flow path by evaluating tracer results, melt core, packing pressure and clamp tonnage, and volumetric shrinkage development. As we saw in this lesson, low pack pressure profiles have the smallest volumetric shrinkage ranges, but on the other hand, they can result in sink marks, voids, and other possible surface imperfections. Finding the right balance is key. By optimizing the process parameters, all other quality criteria can be optimized as well.
Okay, so what we've just learned in this lesson was very important, that the packing pressure, switchover point packing pressure, causes a packing flow. That packing flow will determine volumetric shrinkages, which will determine, yes, you guessed it, dimensional stability in the part. So it is important to understand this behavior to make the right choices at the molding machine, okay? So that's what we have today. Keep in mind the circle of knowledge, part design, mold design, processing. You've probably sensed that we incorporate in every lesson, challenges for all of these three fashions to learn, to understand, and to work with. Yeah, so that's what we're here for. It's a knowledge-based system. If you have any questions, concerns, you see on the screen, Kruse analysis, Kruse training, please don't hesitate to contact me anytime you want. I'm here to help, and thank you for participating. Next month, we have another version of the webinar. Take a look at the website. It's November 18. And one more thing, which is maybe interesting for you to see. We have a YouTube channel, and on our YouTube channel, I want you to look at this lesson here, Understanding Cause and Effect Behaviors in Injection Molding. We have this up for a week now, and over 700 of you have looked at it and found this very valuable. It's a 20-minute presentation I have given to a specific company about DFM, DOE, how to integrate all of that into a strategy to be more successful. So please take a look at that, don't forget. And I wish you a good end of the week, and I'll talk to you soon. Thank you very much. Have a great day. Bye-bye.